The Big Bang Theory has lost some validity in light of new data. The James Webb Space Telescope has found it. We have just made a surprising discovery that is changing the world of physics. The most recent picture taken by this telescope has produced persuasive arguments that have taken experts aback, putting a stop to too much speculation. The telescope's most recent discovery is visually stunning and able to change our comprehension of the cosmos. The experts' discussions regarding this image revolve around the perception of the universe. The stunning shot taken by the James Webb Space Telescope challenges our understanding of the universe. One of the most pressing issues in astrophysics, the universe's age and the rate at which it is expanding, is addressed by this finding. This has left generations of scientists perplexed, leading to extensive studies in search of answers. Cosmologists study where the universe came from, how it works, how it has developed over time, and in what ways it could end. Over the past century, this field has seen great advancements. The generally accepted view in cosmology is that the universe began about 13.8 billion years ago, starting from a dense and extremely hot state. The constant detected by Hubble, the Hubble constant, indicates the speed at which the universe is expanding. But figuring out how to measure it is not straightforward. There are two primary local measurements, including those from the early universe. Stars and Type Ia supernovae are used as standard candles because their constant brightness allows astronomers to determine their distances and, as a result, compute the Hubble constant. By studying how the universe expands over time, scientists can refine their measurement of the Hubble constant. There are primarily two approaches. 1. Measurement of the early universe using the cosmic microwave background CMB radiation discovered in the 1960s as the glow left over from the Big Bang. This microwave energy comes from when the universe was only 380,000 years old. Astronomers can determine the age of the universe and its rate of expansion by noting the minute ripples in temperature and polarization released by the CMB. However, there is a problem. The results from these methods do not match. Local measurements indicate the universe is growing at a rate faster than the CMB data suggests. Researchers have been working hard to figure out why the results vary. Based on measurements, we still do not fully understand all of the warning signs or whether there are mistakes in one or both methods. However, thanks to the James Webb Space Telescope, we can now see deeper into the darkness of space than ever before, revealing planets, elements, and galaxies we never thought possible. Scientists had hoped the data would help them determine the Hubble constant, but the first set of data has shown findings that are inconsistent with pre-existing expectations. Can this information give us new insight into space? We might need to rethink our understanding of the workings of the universe. We could find forces and particles never before seen. Or we might discover that the unknown force known as dark energy, which speeds up the universe's growth, requires reconsideration. With each new piece of information, our ideas about space change. For instance, the cosmic microwave background radiation discovered in 1965 provided solid evidence for the Big Bang Theory. Before that, many scientists believed the universe had always existed and expanded at a constant rate. New evidence, however, demonstrated that this was not true. In the late 1990s, scientists discovered that the universe's expansion was accelerating, a finding that also led to the discovery of dark energy. Each time we test something new, we compare it with what we already know and discover new ways to comprehend the entire cosmos. Without this process, the problems we face in cosmology might not lead to greater understanding. Although difficult, this issue is exciting because it drives the development of better tools for space exploration. Researchers worldwide are intrigued by this cosmological puzzle because everyone wants more knowledge about the universe. Most significantly, it shows that science is constantly changing as we gain new knowledge about space. Another concept is age tension structure, closely linked to Hubble tension, which refers to the distribution of matter in the universe. We use this data to map the universe's structure and examine how it has developed over time. Some parts of space contain many galaxies grouped together, while others are relatively empty. Scientists use various approaches to determine the extent of this dispersion. One approach is to study how clusters of galaxies bend light from faraway galaxies, a phenomenon known as gravitational lensing. This allows us to study dark matter, which does not emit light and is otherwise undetectable. Researchers have also studied the CMB, the cosmic microwave background, the afterglow of the Big Bang. It has taken this light about 13.8 billion years to reach us. By studying the CMB, scientists can understand how the universe was filled with small irregularities in its early stages. However, current CMB data does not match the large-scale irregularities we observe today. The non-spherical distribution of gravity suggests that the early universe was more uniform than it is now. Gravitational lensing observations imply that something fundamental is missing from our interpretation, bringing us back to the mystery of dark matter and its role. Rice and his team, using the Webb Space Telescope, sought to investigate whether a potential error in the Hubble Space Telescope's measurements might explain the discrepancy. However, the JWST showed identical deviations, which is concerning. Somewhere between these two sets of observations must lie a fundamental error in our understanding of the universe. In an interview with an astronomy magazine in the United States, Rice stated that these results are forcing cosmologists to reconsider what we think we know about the cosmos. Making use of the new area, we can now see further into the universe thanks to the telescope via its razor-sharp infrared camera to measure cosmic distances with ever-increasing precision. Both dark energy and dark matter are mysterious elements that constitute a significant part of the universe. Despite this, their nature remains obscure. Black holes, on the other hand, have been the most prevalent explanation for gravitational effects, but new findings are challenging that view. There is growing interest in exploring how dark matter and dark energy may impact these cosmic occurrences. Please share your opinion in the comments box. If you want the video, don't forget to like and subscribe. I'm so grateful for your support, and I'll see you in the next one. As scientists continue to analyze data from the James Webb Space Telescope, which laid the groundwork for modern cosmology, it is now facing a level of scrutiny unlike any before. The telescope's ability to observe far-off galaxies from only a few 100 million years after the Big Bang has posed a challenge to existing galaxy formation models. In contrast to past assumptions, the early universe appears to have hosted larger, more mature galaxies than anticipated. These results suggest that galaxy formation occurred much more quickly than previously believed, or that our understanding of the physics governing the early universe needs to be completely revised. One new theory to explain these discrepancies involves modifying the current version of the lambda CDM model, the standard cosmological model that includes cold dark matter CDM and a cosmological constant lambda representing dark energy. Some physicists propose that dark energy may not be constant at all, but may instead change over time or interact with dark matter in unknown ways. This dynamic form of dark energy, sometimes referred to as quintessence, could account for variations in cosmic expansion rates observed at different epochs. Various other studies are exploring alternative models of gravity, such as modified Newtonian dynamics Mont or scalar tensor theories, which propose changes to Einstein's general theory of relativity at cosmological scales. These theories attempt to explain phenomena such as gravitational lensing and the formation of cosmic structures without invoking unidentified entities like dark energy or dark matter. While controversial and not yet widely accepted, these concepts reflect scientists' growing willingness to re-examine past assumptions in light of new observations. The JWST has also opened opportunities to examine the chemical composition and atmospheres of a group of exoplanets, some of which orbit within the habitable zones of their stars. These studies may not directly affect our understanding of cosmological expansion, but they provide important context for the evolution of matter, star systems, and the possibility of life in the universe. The chemical signatures in exoplanet atmospheres detected by JWST can also shed light on the broader distribution of elements in the cosmos. Another significant piece of the cosmological puzzle is inflation, the extremely rapid expansion of the universe thought to have occurred just fractions of a second after the Big Bang. The inflationary model explains why the entire universe appears uniform in structure despite the vast distances between regions. However, the exact mechanism behind inflation remains speculative. Various models exist, including those involving scalar fields and quantum fluctuations, but no single theory has yet been confirmed by observational evidence. New data from the James Webb Space Telescope may provide fresh perspectives on the inflationary epoch. By studying the distribution and structure of the earliest galaxies, researchers hope to uncover patterns that either support or challenge specific inflation models. If anomalies are discovered, such as unexpected clustering or irregularities in the cosmic background, this could point to physics beyond the standard model. Meanwhile, theoretical physicists are working toward unifying quantum mechanics with general relativity, one of the greatest challenges in modern science. A successful quantum theory of gravity could revolutionize our understanding of the universe's origins, including the true nature of the Big Bang. String theory and loop quantum gravity are two major approaches, but both remain highly speculative due to a lack of direct experimental evidence. Each of these efforts, whether observational or theoretical, points to one overarching truth: our understanding of the universe is still evolving. The James Webb Space Telescope has not only deepened the mysteries of the cosmos, but also given us the tools to ask better questions. As more data becomes available, particularly from long-term missions and complementary tools such as the Euclid Space Telescope or ground-based observatories like the Vera C. Rubin Observatory, we may soon be on the verge of a brand new cosmological paradigm. Until then, the tension between different measurements of the universe's expansion rate and the profound implications of those differences will continue to drive debate, innovation, and discovery in the scientific community. What comes next may not only alter our understanding of the universe's history, but also its future.